In section 5.4, we introduced triple integrals, and we talked about integrating, changing the order of integration to find the one that was simplest or most straightforward to solve. In this section, 5.5, we want to take a look at triple integrals again, but we want to take a look at certain kinds of domains that might be better represented by either cylindrical coordinates or spherical coordinates. We've broken this particular section up into two videos, where the first covers triple integrals in cylindrical coordinates. Let me share my screen and we'll get started. We're going to start with a brief review of cylindrical coordinates. Remember that cylindrical coordinates are based upon the polar coordinate system, which of course we did review when we were working in section 5.3. What we found in this case for cylindrical coordinates is that we extend the polar coordinate system into the third dimension by adding z to the polar coordinates. This gives us ordered triples r, theta, and z. In the cylindrical coordinate system, we can represent that point in space with r, theta, z, where r, theta are the polar coordinates of the point's projection into the xy plane, as if the point is casting a shadow down into the xy plane, which is also our r theta plane. Z is the usual z coordinate from the Cartesian or rectangular coordinate system. This gives us a right triangle which lies in the xy plane. The hypotenuse of the triangle is r, and theta is the angle measured between the positive x-axis and r. Remember that r is the distance from the pole out to the point. In this case, our point is xyz, or r theta z. It casts a shadow down into the r theta or xy plane. Then we measure r from the origin out to that projection of that point, and we measure theta from the positive x-axis counterclockwise until it reaches r. In a sense, this gives us a sort of cylinder, which you can see in the image on the right. And when you're looking at this, you can tell that you get a circular base based on r and theta, and then the height pulls it into the third dimension, creating basically a right circular cylinder. We have formulas to help us convert from cylindrical coordinates to rectangular coordinates and vice versa. If we want to convert from cylindrical coordinates back into rectangular, remember that we have the equation x equals r cosine theta, y equals r sine theta, and z, of course, just stays z. To convert from rectangular coordinates into cylindrical coordinates, remember that x squared plus y squared equals r squared, coming from the polar coordinate system, and tangent of theta is y over x, again coming from the polar coordinate system, and z is just z. The cylindrical coordinate system is very, very similar to the polar coordinate system. We can also use that the radius r is the positive square root of x squared plus y squared, since we generally allow r to vary from 0 to some positive value. And we can also represent theta as the arctangent of y divided by x. We're generally going to limit the value of theta to between 0 and 2 pi, and we're going to use the coordinates of x, y, z to determine which octant it occurs in. Really, we just need the quadrant in the xy plane, since r theta is projected into the xy plane. In this case, when we have rectangular coordinates x, y, z, the equations x equal a constant, y equal a constant, and z equal a constant give us three unbounded planes parallel to the yz plane, the xz plane, and the xy plane, respectively. With cylindrical coordinates, let's remind ourselves of what the different equations represent. When we're in these cylindrical coordinates, The equation R equals C basically gives us a circle, a circular cylinder, which you can see here, which is going to be symmetric about the z-axis. The equation theta equal to some angle alpha gives us a half plane extending in that direction. And the equation z equal to a constant is still a horizontal plane parallel to the xy plane, but at location z equal to the constant. Let's go ahead and look at the table that gives us some of our common graphs in cylindrical form. I have both rectangular form and cylindrical form listed in the table. The first is a circular cylinder, x squared plus y squared equals some constant squared, where the constant is, of course, the radius of the circle. In cylindrical form, this becomes a circular cylinder, r equals c. Then we can look at a circular cone, which you will see in the image below here. If we're looking at a cone, remember a cone is really a double napped cone. It's sort of what we think of as a cone, two of them touching tip to tip. The equation for a circular cone in rectangular coordinates is z squared equals c squared times the quantity x squared plus y squared. In the cylindrical coordinate system, this becomes z equals cr, some constant times the radius, like 5r. And that will give us this circular cone. A sphere is another object that we can work with cylindrical coordinates, though it makes more sense to use spherical. The sphere in the rectangular system is x squared plus y squared plus z squared equals c squared. And since x squared plus y squared is r squared, in the cylindrical system, it's r squared plus z squared equals c squared. Finally, we have one more example of a suitable function for use with cylindrical coordinates, and that would be a circular paraboloid. When we're looking at a circular paraboloid, the equation in rectangular form is z equal a constant times the quantity x squared plus y squared. Since x squared plus y squared is just r squared, then the equation for a circular paraboloid in the cylindrical system becomes z equals a constant times r squared. Let's now go ahead and begin to take a look at how we might integrate in the cylindrical coordinate system. We're going to start, much as we did earlier when we were looking at double integrals in the polar coordinate system. Remember, the cylindrical coordinate system is the polar coordinate system with one added dimension in the z direction. So we're going to start with the polar rectangle shape, which is really more like a trapezoid, but with curving arcs for the two bases instead of flat parallel sides. In this sense, we can define our cylindrical box, if you want to call it that, as the set of all ordered triples r theta z, where r is between a and b, theta is between alpha and beta, and the z value is between c and d. So we're extending from r equal a to r equal b, from theta equal to alpha to theta equal to beta, and from the bottom of the box where z equals c to the top of the box where z equals d. Then, of course, we're going to select a point somewhere inside of the box at which to compute the value of our function of three independent variables. Our function will be a function of x, y, z, but we'll have to rewrite it in terms of r theta z, much as we did in section 5.3. When we're looking at this, you can see projected into the plane the polar rectangle shape, which again is very similar to a trapezoid as you allow the change in the radius and the change in theta to go to 0. We're then going to take this region and subdivide it just as we've done before. It's sort of the calculus thing to do. we're going to divide the region between r equal a and r equal b into more slices, creating more curving arcs that divide out this cylindrical box. Then we're going to take the radial lines from theta equal to alpha and theta equal to beta, and we're going to divide that into more radial lines. Finally, we take slices parallel to the xy plane, and we slice it between z equals c and z equal d. This gives us a bunch of sub-boxes or sub-cylindrical boxes. And then we're going to want to find the volume of this sub-cylindrical box. It makes sense, since these will be a type of regular solid where the base is going to be the polar rectangle and the height is the z value, that we can find the area of the base, the polar rectangle, and multiply by z in order to get the volume of a single box. Let's take a look now at what this would look like. Again, we don't have to take a regular partition, but we typically do, dividing the region from r equal a to r equal b into L subdivisions, and the region between theta equal alpha and theta equal beta into M subregions. And we slice it horizontal parallel to the xy plane from z equals c to z equal d using N subdivisions. When we're done, we're going to create the volume of these cylindrical boxes, which you can see one single cylindrical box in the image here, that the change in volume, the differential dV, will be dA times dZ, because we're going to have the change in area of the polar rectangle multiplied by the change in the z value. But we know the change in the polar rectangle is r dr d theta, or r delta theta. And this becomes the cylindrical differential r dr d theta dz. Now, of course, the next thing to do, which is the very calculus thing to do, is to take a Riemann sum followed by a limit as L, M, and N go to infinity. When we take this differential for the cylindrical coordinate system of r, delta theta, delta z, that gives us, of course, the volume of a sub-box. And then we're multiplying by the value of our function of 3 independent variables. As we take the limit, provided the limit exists, we come up with the definition of the triple integral. This assumes, of course, that our function is a continuous function over that box. And we can write that the triple integral over the cylindrical box, which really isn't a box, it's more like a three-dimensional trapezoidal shape, becomes the triple integral of a function of r theta and z times r dr d theta dz. Now, in actual practice, we typically are going to integrate with respect to z first, and then we will apply the polar coordinates. In this case, all the properties that we've studied before still hold. Let's look at how to convert it into an iterated integral, into something we can actually calculate. The triple integral has the differential dV, and it goes over, in this case, a cylindrical box in 3 dimensions. Our function is a function of 3 independent variables, so it's in 4 dimensions, with w equal to some function of r, theta, and z. We can convert the triple integral into a iterated integral by integrating with respect to r, theta, and z. Since it is iterating over a box, then all the limits of integration will be constants, which means that the order in which you write these really does not matter for these particular types of integrals. Any one of the 6 variations of this iterated integral will work. Let's take a look back at the shapes over which it is appropriate to use cylindrical coordinates. When we look at all of these shapes, a right circular cylinder, a circular double napped cone, a circular paraboloid, or a sphere, notice that all of them can be considered to be symmetric about some axis. Now, the sphere can be symmetric around many axes, but you can also consider it to be symmetric about the z-axis. The circular cylinder here is symmetric around the z, but we could also have a circular cylinder symmetric about y or x. The same is true for the double napped cone. In this case, it is symmetric about the z-axis, but we could have a double napped cone that's symmetric about either x or y. And the same is also true of the circular paraboloid, which is also symmetric about the z-axis. This means if it is symmetric about an axis other than z, that we will have to convert our polar coordinates to correspond to that plane. When we think about these, notice that their cross sections are suitable for polar coordinates. The cross section of the cone is a circle, as is the cross section of the paraboloid. The cross section of the sphere is also circles, as is the cross section of the right circular cylinder. Again, if we have a shape that is suitable for polar coordinates, namely something that is circular or perhaps elliptical, then we need to consider what axis it's symmetric about. If it's symmetric about the z-axis, then the projection into the plane will be into the xy plane, which means that we can use polar coordinates as originally written. However, if it is symmetric about the x-axis, then the projection will be into the yz plane, in which case we need to convert the polar equations to correspond to the yz plane. Y takes the place of x, becoming r cosine theta. Z takes the place of y, becoming r sine theta. Y squared plus z squared is r squared, and tangent of theta is given by z, the dependent variable, over y, the independent variable. Likewise, if we have a region that is symmetric about the y-axis, some surface, then we need to convert the polar equations to reflect what the projection will be in the xz plane. In this case, x remains r cosine theta, but z takes on the y role as r sine theta. Then we have x squared plus z squared is r squared, and the tangent of the angle is z divided by x. Let's now go ahead and take a look at our first example. In our first example, we are in fact integrating over a cylindrical box. How do you know that this is a cylindrical box? First off, notice that you have a triple iterated integral, and you have the differentials dz, dr, d theta. The only time you're going to get dz, dr, d theta is when you're in cylindrical coordinates. Notice also that our differential is r dz, dr, d theta. We do typically do dz first, but in the case of a cylindrical box, since all the limits of integration are constants, it does not matter what order you do the integration in. Let's take a look at what this particular shape looks like out on CalcPlot 3D. And of course, when we're talking about the shape, we're talking about the domain. We're not talking about the function of three independent variables because we can't graph easily in four-dimensional space. This is the region that we're talking about integrating over. This is our domain. It's a half cylinder, and it's going from z equals 0 to z equal 4 with theta restricted between 0 and pi. Let's take a look back at the limits of integration and see if that makes sense. Z is from 0 to 4, theta is from 0 to pi, and we didn't measure the radius in CalcPlot 3D, but it is indeed from the pole, the origin, out to r equal 1. Go ahead and pause the video now to work out this integral, then turn it back on so we can work it together. Note that I went ahead and rewrote the integrand by pulling the r from the differential into the integrand. This becomes r squared z sine of theta. I chose to integrate with respect to z first because I know that's going to be my habit continuing forward. When I integrate z, the r squared sine theta remains constant, and the integral of z becomes 1/2 z squared multiplied by r squared sine theta. Evaluate between z equals 0 to 4 to give us 16 multiplied by the 1/2 r squared sine theta, which gives us a new integral for the outside of 8r squared sine theta. The next one I want to integrate with respect to is r. Again, because this is a cylindrical box, I could go in any order I like. However, I know moving forward that z will likely be a function of r and or theta. R will likely be a function of theta, and theta will generally be constants. In this sense, I know that in the future, I'm going to want to integrate with respect to z, then r, then theta. So I'm just making it my habit. When I integrate r squared with respect to r, I get r cubed divided by 3 multiplied by the 8 sine theta. I evaluate this between r equals 0 and 1 to come up with 8/3 sine theta again. 8/3 sine theta, when I integrate sine theta with respect to theta, I get 8/3 cosine theta, which I evaluate from 0 to pi. The cosine of pi is -1 and cosine of 0 is 1, so -1 minus 1 is -2. However, I got a negative, so -8/3 times -2 gives me 16/3. It's not possible to interpret what this is until we know what the function of 3 independent variables represents. It could represent something like pressure at a particular point in space, in 3-dimensional space. Now that we've taken a look at this, let's talk about integrating over a general region and not just a cylindrical box. As you are well aware by now, we typically want to integrate over blobs in 3-dimensional space. So again, we'll let the letter E represent our domain in R3 over which we're integrating, otherwise known as the blob. And D will be the projection of that blob onto the r theta plane. Now remember that the r theta plane could be in the xy plane, the yz plane, or the xz plane, depending upon which axis the shape is symmetric about. Be sure to use the widest part of the blob to cast the shadow. That widest part is often found at the intersection of 2 or more surfaces. Let's go ahead and look now at what's going to happen. For typical cylindrical coordinates, which is symmetric about the z-axis, this means that D is really just a subset of the xy plane or the r theta plane. But again, we can project into either yz or xz as needed. In this case, because it's now a general region, z will be a function of r and theta. Our surface will go from some surface of r theta to another surface of r theta. Then r will go from some function of theta, g1 of theta, to a different function of theta, g2 of theta. And finally, the outer integral goes between constants, theta equal to alpha and theta equal to beta. Notice that the innermost integral is a function of the 2 variables in the differential outside of it. The middle integral is a function of the variable in the differential outside of it. In a case of a general region, you have to put them in the order for which the functions are Well, functions of. Since z is a function of r and theta, it has to be done before we can integrate with respect to r and theta. Since r is a function of theta, we have to integrate with respect to r before we can integrate with respect to theta. We could also represent these around the other two axes as well. Let's take a look now at example 2. In example 2, we are not trying to actually compute the integral because we're not told what the function of r, theta, and z is. However, we're asked to set up an iterated integral to represent a triple integral over a particular restricted solid in three-dimensional space. Our solid, E, is represented by the region inside a right circular cylinder with equation r equal 2 sine theta, bounded below by the r theta plane, which is really just the xy plane, and bounded above by the slanted plane z equal 4 minus y. Let's take a look at a picture so we can get a better understanding of what we're looking at. In the image on the left, you can see that we have a slanted plane coming down through our right circular cylinder. The circular cylinder is cut off at the bottom in the xy plane. If we visualize then what this will look like, we have the slanted plane for the top, the xy plane for the bottom, and it's inside of the circle where the radius depends on that function, which I believe was 2 sine theta. Yes. Let's look at it in CalcPlot 3D. In CalcPlot 3D, our original shape, of course, looks something like this. Notice that the cylinder is going all the way through the plane, and we want it to stop at the xy plane. When we look at this, don't forget that you can use BSP triangulated to smooth out the edges between the plane and the circular cylinder. When we restrict to a region by plotting, by selecting region, and then selecting polar coordinates on the inside, we know that the outer regions of our radius are given by the function 2 sine of theta. This does, however, touch the pole, so our inside radius is 0. We want to go all the way around our shape, so we're going to allow theta to go from 0 to 2 pi. The top of our surface is given by the slanted plane with equation z equals 4 minus y, and the bottom surface is the xy plane given by z equals 0. In some ways, this sort of reminds me of, well, a tube of lipstick with a slanted top. Let's now consider how we can write what the iterated integral would look like. Let's go ahead and write down what we've determined thus far. We know that z is going to be greater than equal to 0 and less than equal to the slanted plane, which I believe was 4 minus y. We also know that r is going to vary between the pole and the outer limit 2 sine of theta. We know that theta is going to vary between 0 and 2 pi. This should allow us to write the iterated integral, even though we don't know what the integrand function is. We'll do theta last because it is not a function of any other variable. This goes from 0 to 2 pi with respect to theta. On the inside, in the middle integral, we have r equals 0 to 2 sine of theta. And then we have inside of that the integral from z equals 0 to z equals, now we're in trouble. We have a bit of an issue here because z is going to go up to 4 minus y, but y is not one of the variables in my outer two integrals, so I need to convert. I can rewrite the y as r sine theta. And this now writes z as a function of r and theta, 4 minus r sine theta. And that definition is coming from polar coordinates. We don't know what our function of r theta z is, but if we did, it would go in the integrand, followed by, and maybe I should move this over a bit, followed by the differential for dz, and then our r dr d theta. Notice that you can move the r to the inside innermost integrand, since z is also a function of r. Notice here that our upper limit of integration for z is a function of both r and theta, the two integrals outside of it. Our central integral is a function of theta, which is the integral outside of it. We'll have to integrate in this order to compute the triple integral over this general region. Now let's take a look at example 3, where we are told what our function is, and we actually want to integrate and find the true value. We're told that our solid, our blob in three-dimensional space, which is the domain over which we're integrating, is the region bounded by z equals 2x squared plus 2y squared minus 7, which of course is a circular paraboloid pulled down 7, and the plane z equal 1, which is just horizontal and parallel to the xy plane. You can see what E must look like over here on the left. E consists of the part of the paraboloid below the plane x equal 1. The widest part of that solid is going to be where the plane intersects the paraboloid, which is when z is equal to 1. So we can look at this and tell that from the perspective of integrating with respect to z, on the bottom we have the paraboloid, and on the top we have the plane. We want to be able to write the limits of integration for z, but we will eventually have to convert them into something in terms of r and theta. To start with, we can say that z goes between the paraboloid, which is 2x squared plus 2y squared minus 7. It's a little tight. Less than equal to z, and less than equal to the plane z equal 1. Again, I have the z-axis pointing straight up, so I can tell which surface is below and which surface is above. However, this is written in terms of rectangular coordinates. To write it in terms of cylindrical coordinates, I need to replace x and y. You could replace them with r cosine theta and r sine theta, but it's easier if you recognize that you have a common factor of 2 on the first two terms, which allows us to then write this as 2r squared minus 7 less than equal to z less than equal to 1. The 1, of course, is a constant, so it doesn't need to be converted. This gives us our innermost limits of integration, where one of them is a function of r, which will be our middle integral. Now we need to find out what it looks like for the outer limits of integration. This is coming from the widest part of our three-dimensional solid over which we're integrating. That widest part is at the intersection of these two. We need to find an equation for that so we know what the shadow cast into the r theta plane will look like. When z equals 1, we can write that we have 1 equal to 2x squared plus 2y squared minus 7. Move the 7 to the opposite side and then divide everything by 2. This gives us the equation 4 equal x squared plus y squared, which of course is a circle of radius 2. This means the projection into the plane is going to be a circle of radius 2. If we want to go all the way around the circle, then theta needs to vary between 0 and 2 pi. To get all of the inside of the circle, r needs to vary from 0 to 2. And this will give us our limits of integration for the outer two integrals. And theta goes between 0 and 2 pi. Notice that this time, r is not necessarily a function of theta. However, you do want to do it in the order that we have established thus far if r is a function of theta. If all of these are constants, then it doesn't matter which order you do them in. Let's take a look at what it would look like on CalcPlot 3D. On CalcPlot 3D, you can see that I've graphed it as a region where r goes between 0 and 2, and theta goes from 0 to 2 pi. The top of my surface is the plane z equal 1, and the bottom is the paraboloid written in terms of x and y for CalcPlot 3D. If I show the prisms, you can see the polar rectangles as the purple shapes on the top of this solid E. And when we look at it out on CalcPlot 3D, we'll be able to get an estimation of the volume. Go ahead and pause the video now, represent the triple integral as an iterated integral, and calculate. Make sure that when you set up your iterated integral that you do convert the integrand for xy into a function of r and theta. This will give you 4 times r cosine theta, r sine theta, or 4r squared cosine theta sine theta. When you incorporate the r from the differential dz r dr d theta, you get 4r cubed cosine theta sine theta dz dr d theta. Our limits of integration for z are between 2r squared minus 7 and 1. There is no z present in the integrand, so we simply get z, and we evaluate at the limits of integration. When we do so, we end up with a new integrand of 8 minus 2r squared. Then we can take this and we can distribute just the r cubed over this 8 minus 2r squared, which gives us 4 times 8r cubed minus 2r to the 5th, the quantity, times cosine theta sine theta. In other words, I'm sort of isolating everything that depends on r inside one factor. The 4 cosine theta sine theta is just a constant, so it does not affect the integration. When I integrate 4r cubed minus r to the 5th, I get r to the 4th minus 1/6 r to the 6th. I evaluate from 0 to 2, and I get 16/3 multiplied by the constant factor, 8 cosine theta sine theta. Finally, this gives me 128 over 3 cosine theta sine theta with respect to theta, where theta goes from 0 to 2 pi. I can do a u substitution where u is sine theta and du is cosine theta d theta. But when I change the limits of integration, they both become 0. When you integrate from a constant to the same constant, you end up with 0 area between, well, itself and itself. So there's no area under the curve, so the value of our triple integral is 0. Again, until we know what the function of 3 independent variables represents, it's hard to interpret this result. Let's now turn to example 4. Example 4 is rather tricky to set up in CalcPlot 3D. We have a function of 3 independent variables, the exponential e raised to the power negative x squared minus z squared. E is the space between 2 circular cylinders, x squared plus z squared equals 4, and x squared plus z squared equals 9, with more restrictions on y and z, y between 1 and 5, and z less than or equal to 0. When we plot this on CalcPlot 3D, we can get what amount to two half cylinders. X squared plus z squared equal 4 is a circular cylinder of radius 2, and x squared plus z squared equal 9 is a circular cylinder of radius 3. Both cylinders are symmetric around the y-axis. So we'll get our projection into the xz plane. This means we'll need to integrate with respect to y first. When we're thinking about it, when we restrict between y equal 1 and y equal 5, we're slicing through with a plane at y equal 1 and a plane at y equal 5. We get the half circle cylinder shapes that you see here. CalcPlot 3D doesn't have a way of drawing the region when you can't represent it in terms of z. In this case, if we look at it with the y taken out by using Alt-Y, and we look at it in the XZ plane, we can see that we've got two cylinders, and the region we're talking about is the region that is in between the two, which I've now shaded yellow. One of those semicircles has radius 2, and the other has radius 3. In the image on the right, with the orange half circle on the front, you can see the actual solid. This was produced using Wolfram alpha. When you look at this, notice that the projection into the XZ plane, the widest part of our shape, is always going to be the shape that you see here on the left, now highlighted in yellow. It's going to go from the radius of 2 out to the radius of 3, and it looks sort of like a horseshoe shape. When we look at this, we can call this a half of a ring or a half of an annulus. When we think about the annulus, remember that we have cut off where y equal 5 and y equal 1, but on both ends, the shape is the same size and same shape. So when we cast our shadow, we do get the shape that you see here, graphed in orange. Now we'll need to decide what r varies between, what theta varies between, and what y varies between. In the case of this particular graph, when we're looking here, we can see that r is varying between 2 and 3. Theta is going from pi around to 2 pi, restricted to the xz plane. That means that to use the polar coordinates, we will have to rewrite them using the substitution factors that x is r cosine theta and z is r sine theta. What about with respect to y? If we were to rotate it so that we have the y straight up and down, and let's take a look at it here. If I rotated it so that y was straight up and down, what would the shapes be for the top surface and the bottom surface? Let's take a look at the cylinders out there on CalcPlot 3D. When we look at the two half cylinders out here on CalcPlot 3D, we want to use the image with y pointing directly up in order to determine what the lower surface and upper surface is. In this case, we can go ahead and take z out of it and rotate. When we look at it from this viewpoint, when you're looking here, you can see, oops, wrong direction. So let's rotate about y. When I'm looking at it, can you see that at the lower surface, we have the plane y equal 1, and at the upper surface, we have the plane y equal 5. That means the limits of integration for y will be from 1 to 5. Let's go ahead now and set up the iterated integral so that we can calculate. Notice that in order to convert the triple integral over region E, we have to convert the integrand. We know that it's symmetric about y, which means that our projection will be in the xz plane. That means we're going to use polar coordinates converted to the xz plane. Factoring out the negative gives us e to the negative r squared, since r squared replaces x squared plus z squared. Notice also that when we set up the iterated integral, all the limits of integration are in fact constants. What does this mean to you? This means that we're actually integrating on a cylindrical box. Let's take a look at the region again up above and verify that it is in fact a cylindrical box. When you look at the shape here, you can see that it is in fact a polar rectangle being drawn into the third dimension, but along y instead of along z. In this case, it is in fact a cylindrical box. Go ahead and pause the video now to work out the solution, then turn it back on, and we'll look at the integration together. Note that we need to convert the integrand, and it becomes e to the negative r squared. Our differential first is dy, but then our outer differential is r dr d theta. We could rewrite this as r e to the negative r squared dy dr d theta. Since there is no y present, then when we integrate, we get r e to the negative r squared y evaluated between 1 and 5, which introduces a factor of 4. The new integrand is 4r e to the negative r squared dr from r equal 2 to 3, then the integral with respect to theta from pi to 2 pi. We can do a u substitution where u is negative r squared, du is negative 2r dr. So 2r dr, which is a part of the 4r dr, becomes negative du. When we change the limits of integration, when r is 2, u is negative 4. When r is 3, u is negative 9. This introduces a negative into the integrand, but since the limits of integration are backwards anyway, we can switch the limits of integration and remove the negative. This gives us the integral 2 e to the u du from u equal negative 9 to 4. When we integrate e to the u du, we just get e to the u. So when we evaluate, we get 2e to the negative 4 minus 2e to the negative 9. There's no theta present in the integral, so when we integrate, we get theta. Evaluating theta between pi and 2 pi gives us a pi, so our final result is 2 pi times the quantity e to the negative 4 minus e to the negative 9. We have one more item that we want to cover before we complete this particular video on cylindrical coordinates used in triple integrals. And that is, how can we use cylindrical coordinates to compute the volume of the domain over which we're integrating? We'll do what we've been doing in the past, and we'll allow the integrand to be a positive 1. Let's take a look at example 5. In example 5, we want to use a triple integral with cylindrical coordinates to find the volume of the solid domain bounded by the slanting plane z equals 6 minus x, the half cone z equal negative square root of quantity 4x squared plus 4y squared, that's inside the cylinder x squared plus y squared equal 3, with x limited to being less than equal to 0. This is going to cut our cylinder in half so that we don't get the full circular cylinder, we just get half of it. If we take a look at what this looks like out on CalcPlot 3D, you can see that you do have a half cylinder, you've got a slanting plane coming through it, and a downward opening half cone, which is sticking up inside of the half cylinder. Let's go ahead and look at it from CalcPlot 3D's point of view so we can rotate it and get a better view. Notice how it comes up inside of that half cylinder, and it produces a sort of a circular slanting top on our solid. The solid is going to come below the plane, but above the cone. The cone is sticking up in the center of that half cylinder. Let's go ahead and plot the region by thinking about what our various variables have to vary between. We know that the top of the surface is given by the slanted plane and the bottom of the surface is given by the cone, which is sticking up inside. It does have to be inside the circular half cylinder, so we know that R is going to vary from 0 out to the radius of the half cylinder, which is square root of 3. Let's take a look at what it looks like with the restricted area. When we look at this one, we can see that we're varying R from 0 to the square root of 3, and we're varying theta from pi over 2 to 3 pi over 2. This gives us only x values that are less than or equal to 0. This means that we are integrating across quadrants 2 and 3. That's where x is less than or equal to 0. The top is our slanting plane, 6 minus x, and the bottom is our half cone, negative square root of quantity 4x squared plus 4y squared. When you look at the region over here, you can see the slanting top from the plane cutting through. Then it's solid, except for on the bottom, the cone has, well, taken a chunk out of it, if you will, and it looks like this. Let's now go ahead and use this information to represent the iterated integral. When we're representing the iterated integral, remember that we want z to go between the half cone and the surface, which is the slanted plane. We also need our radius to go from 0 to the square root of 3 and theta to be between pi over 2 and 3 pi over 2 to limit it to the region where x is less than or equal to 0. Pause the video to write down the triple integral converted into an iterated integral, then turn the video back on so we can compare. Don't forget, you also need to convert the integrand. In this particular problem, because we're trying to use cylindrical coordinates to find the volume of the region over which we're integrating, our integrand is in fact 1. So there's no actual conversion to take place. However, notice that our limits of integration with respect to z, around which our region is symmetric, do depend on x and y, so these must be converted. On the bottom, we have the half cone, and on the top, we have the slanted plane. We need to convert each of these into a function with respect to r and theta. When we convert the half cone, we can factor the 4 out from under the radical and get 4 times quantity x squared plus y squared, which becomes 4r squared. Since we're going to allow r to vary from 0 out, this gives us negative 2r as the new lower limit of integration with respect to z. The upper surface is given by the slanting plane 6 minus x. So we replace x with r cosine theta to get 6 minus r cosine theta for the innermost limits of integration with respect to z. Notice that I moved the r from the r dr d theta differential inside into the main integrand. The integrand then just simply consists of r dz dr d theta. So since I don't have a z, when I integrate, I get r times z. I evaluate this between the limits of integration that depend on the variables in the outer two differentials, r and theta. When I simplify this, I can rewrite it as 6r minus r squared cosine theta plus 2r squared. I have two terms that have r squared, and since I know I'm going to integrate with respect to r next, I can factor the r squared out of those two terms to give me only two terms. This just cuts down a little bit on the integration you have to do. When I rewrite it, my new integrand is 6r minus r squared times the quantity cosine theta minus 2. R is varying from 0 to square root of 3. When I integrate 6r, I get 3r squared. When I integrate r squared, I get r cubed over 3, still multiplied by the constant factor. In this case, I evaluate from 0 to the square root of 3 for r. When I simplify the first term, I get 9. When I simplify the next one, I get 3 square roots of 3, which when multiplied by the 1/3 cosine theta minus 2 is going to give me square root of 3 times cosine theta minus 2. Finally, I went ahead and multiplied everything out so that I could isolate any terms that had theta in them. This gave me 9 plus 2 square roots of 3 minus square root of 3 times cosine of theta. I grouped my 9 plus 2 square roots of 3 together, since that's just a constant that doesn't depend on theta, so that when I integrate again with respect to theta, I only have 2 terms. When I integrate, I get 9 plus 2 square root of 3, the quantity, times theta, evaluated between pi over 2 and 3 pi over 2, which is going to give me pi. This gives me 9 plus 2 square roots of 3 times pi. When I integrate cosine of theta, I get sine of theta with the constant factor negative root 3. I evaluate between pi over 2 and 3 pi over 2, and when I simplify, I get 2 square roots of 3. This gives me a final result for the volume of this object, this 3-dimensional blob that we are using as the domain for this particular triple integral. 9 plus 2 square roots of 3, all divided by pi, plus 2 square roots of 3. This concludes our study of triple integrals in the cylindrical coordinate system. In part 2 of the video series over section 5.5, we'll take a look at triple integrals with the spherical coordinate system. See you soon for the next video.